Welcome to today's explainer. Let's dive right into decoding what I like to call the beautiful interconnected language of triangles. So often we look at trigonometry or geometry and we just see this massive wall of intimidating equations. But what if I told you that every single one of those equations actually tells a really simple, elegant story? Today, we are building the Triangle Explainer, and we're going to focus really closely on the actual text in this explainer. The text of these formulas, that is. I want to show you that math absolutely isn't just some arbitrary list of scary rules you have to blindly memorize. No way. It's actually a highly logical language. It's a way of translating physical shapes, like sides and angles and areas, into readable text. And once you grasp the grammar of this language, triangles completely stop being puzzles and start becoming perfectly legible sentences. Okay, here is our roadmap for today. Section 1 is the triangle alphabet. 2 is sine and cosine rules. 3 is the geometry of shadows. 4 is the half-angle family. 5 is Heron's formula. And finally, section 6 is 3 big ideas. Let's get right into it. Section 1, the triangle alphabet and our foundational variables. Right, so before we can speak any language, we actually need some letters, right? In our triangle alphabet, lowercase letters, little a, b, and c, represent physical sides. Uppercase letters, big A, B, and C, represent their opposite angles. But our true foundational anchor is this concept of the semiperimeter. It's represented by a lowercase s. And the definition is just beautifully simple. You literally add all 3 sides together and cut the answer in half. So for instance, if you've got a triangle with sides measuring 3, 4, and 5, you add those up to get 12, cut it in half, and your semiperimeter S is 6. Keep a close eye on S today, because it's essentially the secret key that's going to unlock our most advanced formulas a little later on. Moving right along to section 2, sine and cosine rules, or what we can think of as the grammar of proportions and corrections. The sine rule simply states that a side divided by the sine of its opposite angle is always the same proportion across the entire triangle. Think of it like this. A side and its opposite angle are a matching pair. If you imagine building a triangle inside a circle, the bigger an angle gets, well, the bigger the opposite side has to become to close the gap. Big angles demand big opposite sides, small angles demand small opposite sides. The sine rule tells us that this specific ratio, side A divided by side A, side B divided by side B, is entirely locked in. It perfectly preserves the proportions of the shape. So, if you know just one side and its opposite angle, you've got your starting pair to literally decode the rest of the shape. Now, this brings us to the cosine rule. You probably recognize the good old Pythagorean theorem, right? A squared equals b squared plus c squared. But what if your triangle doesn't have a perfect right angle? Well, the cosine rule is quite literally just that exact same theorem for any triangle, but with a clever little cosine correction tagged onto the end of the text, minus 2bc cosine A. Imagine holding 2 sticks of length b and c, joined at an angle. If you change that angle, you change the distance between their free ends, which becomes side A. The cosine part tells us exactly how much we need to adjust our Pythagorean calculation to account for that specific, non-perfect angle. It is just such an elegant grammatical correction. Which takes us to section 3, the geometry of shadows and building sides from projections. The source material gives us this wonderfully evocative quote: "A slanted stick casts a smaller shadow." Think about what a projection actually is for a second. Imagine shining a flashlight straight down onto a flat line. If you hold a stick at a slant, the shadow it casts on the ground is obviously shorter than the stick itself. In trigonometry, that shadow is called a projection. And understanding that completely changes how we can calculate a triangle's sides. So, looking at the actual text of the projection rule, it shows us that side A equals b cosine C plus c cosine B. The really crucial takeaway here is that a base side of a triangle can be perfectly built simply by adding together the projected shadows of the other 2 sides. Side B casts a shadow along the bottom, which mathematically translates to b cos C. Side C casts its own shadow, C cos B. Push those 2 shadow lengths together, and they perfectly equal the exact length of side A. It's just a different dialect for describing the exact same geometry we were just looking at with the cosine rule. All right, section 4, the half-angle family, and connecting sides to sliced angles. Now, I know at first glance things look a bit mathematically heavy here, but I promise you, these are really just different dialects of the same alphabet we've been learning, specifically leveraging our anchor, the semiperimeter. The half-angle formulas let us find the exact sine, cosine, and tangent of an angle that has been cut exactly in half. So if angle A is 60 degrees, these formulas let us calculate the properties of a 30-degree slice. But here's the truly amazing part. We can find these sliced angles directly from just knowing the lengths of the three sides. By using our semiperimeter S, which again is just the three sides added together and halved, we totally bypass needing to know the full angles entirely. And the beauty of this family is how they all interact with each other. Tangent of A over 2 is simply the sine half angle divided by the cosine half angle. If you take the complex-looking sine half angle formula and physically divide it by the cosine half angle formula, all the complicated bits like the b and c variables simply cancel each other out. It is not magic, it is just pure logic, leaving behind a beautifully simple, readable tangent relationship made entirely of s's and the side lengths. Which leads us perfectly into section 5, Heron's beautiful area formula, going from sides to total area. Heron's formula is absolute mathematical poetry. The text reads, area equals the square root of s times s minus a times s minus b times s minus c. Normally, finding an area means you need a base and a height, right? Which almost always requires knowing an angle. But Heron's formula bypasses all of that completely. It finds the total area of the triangle using absolutely nothing but our semiperimeter S and the lengths of the three individual physical sides. Let's actually put this into practice with a classic example. Say you have a standard 3, 4, 5 triangle. First, we find S, which we established earlier is 6. You plug that S, along with the side lengths 3, 4, and 5, straight into Heron's formula. So you multiply 6 times 3 times 2 times 1. That gives you 36. Take the square root of that, and boom, it flawlessly resolves to a perfect area of exactly 6 square units. No angles required whatsoever. Do you see how this forms a beautifully connected family tree? These aren't just random equations pulled from a dusty textbook. They're a logical chain of translations. Step 1, we take the physical sides and translate them into a semiperimeter. Steps 2 and 3, we use that to step through the half-angle sines and cosines. Step 4, we logically divide those to find the tangent. And step 5, we use those exact same foundational pieces to arrive at the total area. It's a perfect, unbroken chain of logic. Let's wrap this up with section 6. 3 big triangle ideas and our complete translation. So here is your mathematical toolbox summarized. First, the sine rule. This is your go-to for proportions, proving that a side and its opposite angle stay perfectly synced. Second, the cosine rule, your grammatical correction for finding a missing third side when you only have 2 sides and the angle between them. And finally, Heron's formula, your ultimate shortcut for finding the total area using nothing but the 3 sides. Remember, all of these formulas are simply different ways of describing the exact same underlying geometry. Which leaves us with this final, somewhat provocative thought to consider. We've seen in this explainer that the seemingly intimidating complexities of trigonometry are really just a beautiful, interconnected language waiting to be read. It's all about finding the right text and the right perspective. So if every triangle formula is just translating the same shape into a different dialect, what other complex, intimidating problems in your life are simply waiting for you to find the right translation? Thanks for exploring the triangle language with me today.